Let's look at another way for doing that same problem, 829. A is 35, 16 fifths, and 3. But let's use the method from the book, page, page 298, where we use a property that says f of lambda equals r of lambda. Then we also have function of the matrix itself. So if the eigenvalues satisfy the relationship, then the matrix will also satisfy the relationship, and it's related. It's in the Cayley-Hamilton kind of section. It's a similar kind of idea. And so let's use this method to find our e to the at. This e to the at again can be written as a infinite series, just like in the explanation in the book. So this e to the at function satisfies the requirements that we need for using this kind of a theorem, or this property. Alright, so we're going to say our r, in general we'll call it r of x to start with, is e to the xt, going to be some alpha naught plus alpha 1 x, and continuing on to x to the n minus 1 power. Well, n in our case is 2, so n minus 1 is 1, so we're only just going to go to the power of x. Okay, so we have a simple linear relationship here, and we'll need to go ahead and find our eigenvalues, I guess. We just found them earlier in the earlier part of the problem, didn't we? Yeah, we have our eigenvalues are, let's say, -1 is lambda 1, and 7 is lambda 2. And so we can substitute in to our relationship here for x equals lambda, these two different values of lambda. We can get two linear equations and solve them simultaneously and get our relationship. So let's do for lambda 1 equals -1. We'll say r of lambda is e to the lambda t, e to the -1 t is equal to alpha 0 plus alpha 1 times lambda, which is again -1. Now for lambda 2, which is 7, r of lambda, e to the 7t equals alpha 0 plus alpha 1 times 7. Alright, so we just need to solve these two equations now for alpha 1 and alpha 0. And let's just take the first one. Say alpha 0 equals, bring the negative alpha 1 to the side, e to the -t plus alpha 1. Okay? And then we can substitute into this other, in the second equation, bring it down, e to the 7t equals alpha 0, but now we're going to put in for alpha 0, e to the -t plus alpha 1 for alpha 0 plus 7 alpha. Solve this for alpha 1, so that gives us alpha 1, kind of rearrange sides here, 8 alpha 1 on this side equals e to the 7t minus e to the -t, and so alpha 1 is 1/8 e to the 7t minus e to the -t. And let's use our alpha 0 equation from above. Alpha 0 is e to the -t plus alpha 1, and so plus 1/8 e to the 7t minus e to the -t. Alright, so what does that come out to be? 1/8 e to the 7t, and then 1 minus 1/8, so plus 7/8 e to the -t. Alright. Okay, so we've got our alpha 1 and alpha 0. Now we can put in R of A is e to the AT, but it's also alpha 0. Well, in a matrix equation we need the identity matrix plus alpha 1 times A, the matrix. Now we're putting in the matrix into the polynomial equation. And so we can find the whole idea here is finding e to the AT. So now all you need to do is substitute in there, and I guess I'll let you guys do that. Well, I'll take it a little bit further, but so we'll have 1A e to the 7t plus 7a's e to the negative t, this quantity times identity matrix, and then we add to it alpha 1, which was 1/8 e to the 7t minus e to the negative t times a, original a, 3, 5/16, 3. Okay, so you just carry out the matrix math and you get an expression then. There are no variables left now except for t, which is what we want, and you can get your e to the AT equals some 2 by 2 matrix. So I'll leave the rest for you to do in your homework problem, so you can pick for the problem which way you want to do it.